Do it again. All right, we're ready to go here, chapter 37. The final chapter of ELEC 120. The final chapter of the book. The final chapter. Actually, let me give you the historic perspective on this because this is actually kind of cool. I think it's cool, or I won't be talking about it. I only talk about stuff that's cool. In the beginning, we understood, in ELEC 110, we talked about matter, fundamental building block of nature. We talked about applying energy to matter, knocking an electron loose, then being able to harness that electron. We talked about the fundamental properties of materials and their electrical properties as they relate to the physics of electronics. We talked about current, we talked about voltage, we talked about resistance, we talked about power, we talked about series circuits, parallel circuits, complex circuits. We talked about capacitors, we talked about inductors, those reactive components. We talked about AC power. We talked about AC signals. We talked about reactive components and how they react to AC. We talked about transformers. Then we talked about this whole group of components called semiconductors and how semiconductors could be used to amplify voltage, amplify current, amplify power, control voltage, control current. We talked about the newer generation of transistors, if you will, FETs, field effect transistors. We talked about thyristors. Some of you that were here, we talked about Thimaster. Suzanne Summers, the spokesperson for Thimaster, and Joe Gryniuk, the spokesperson for the thyristor. Those high power devices that are used, solid state devices. We talked about integrated circuits where we get those small transistors and we integrate those onto a circuit and we cram hundreds, thousands, tens of thousands, millions, billions. Intel now is cramming billions of transistors on something the size of a postage stamp. It's crazy. We talked about digital. We gave you an introduction to digital. And digital is everything breaks down into ones and zeros. And then we could have these circuits that are made up of logic gates. Those logic gates are made up of transistors. And those logic gates give us logical, predictable outcomes of the circuits 100% of the times. And that's kind of how digital went. And digital, back in the day, it was good. You know, the digital watch, a digital clock, digital circuitry. It was good. But then what they said is there's got to be a way that it would be nice if we could have a digital circuit that does this, ABC at this moment in time, and then at the next moment in time it does XYZ. And then at the next moment in time, it does ABC again, and maybe ABC again, and then it does XYZ. So one digital device that could do a variety of different things, but have it be one platform. That was really the birth of the microcomputer. So the microcomputer is really the culmination of everything that we've talked about in the past, all coming to a certain point in history where they're able to make a digital device that is programmable and adaptable to run your specific type of application. And it truly is an amazing device. You know, we'll talk about it in this chapter where all we've gone with microcomputers, and like I said, everything has got a computer on board now. So this is really the culmination of years of advancements in digital technology. After completing this chapter, you're going to be able to identify the basic blocks of a digital computer, explain the function of each block of a digital computer, describe what a program is and its relationship to both digital computers and microprocessors. Identify the basic registers in a microprocessor, explain how a microprocessor operates, and identify the instruction groups associated with microprocessors. First of all digital computers, and if I had a nickel or a dime for every time I was asked this question in a professional interview, I'd be a very wealthy individual. No, I'd actually have enough to probably go buy a gallon of gasoline, which would be cool. Hey, gas prices came down today, right? Digital computers consist of 5 basic blocks. Control, ALU, or arithmetic logic unit. Memory, input, and output. Sometimes output is identified as a single block because, quite frankly, you need both of them. I mean, if a computer didn't have the ability to output, I mean, that'd be a cool business plan. Put something together. The ultimate computer. Data goes in, nothing comes out. It really wouldn't work too well. This is the functional block diagram, and to be honest with you, I'm not going to necessarily quiz you on this per se. I'm not going to give you a blank sheet of paper, but my challenge to you is you should be able to draw this on a piece of scratch paper and explain it to somebody. I mean, that's what this class is all about. This is about literacy, technical literacy. The heart of the microcomputer is the ALU. Input feeds input into the ALU, and the ALU feeds the output as well. Memory has to be integrated with input, ALU, and output, and then also you have to have a control mechanism that controls and sequences the input, the processing of the data through the ALU and the output. So, a real simple functional block diagram. The control unit specifically decodes each instruction that enters the computer. Computers are not really smart. Computers are just predictable. And they're predicting, what they do is they process what's known as an instruction. And that instruction is basically coded in memory. So what an instruction is, I don't want to get into the specifics about programming, because quite frankly I hate programming. I was never a programming kind of guy. Programming and Spanish were the two things that I really struggle with in life. No, let's open that up to all foreign languages and programming. Any foreign language. Basically, English is how I roll, period. So if it's programming a computer or, habla español, I crash and burn. Basically, what a computer has the ability to process an instruction. And being a parent, it was kind of interesting watching my kids mature and grow up. You know, when they were really, really small, getting ready for bed was like this whole huge complex scenario. You know, you need to wash up. You need to brush your teeth. Oh, I forgot you don't know how to brush your teeth. Well, you get the toothbrush, you hold it in your hand like this, you apply this amount. This is the motion. Don't forget the back teeth. You know, you should be timing yourself. You need to shut the water off while you're brushing the teeth. Now you need to rinse. How many steps are there in brushing your teeth? It's a pretty complex set of instructions when you come right down to it. So gradually, as your kids, keep your fingers crossed for this one, gradually as they get older, the instructions you give them is a lot less complex. I specifically remember my kids getting up and getting ready for school. You know, you need to set the alarm clock, you need to get up, you need to shower, you need to get dressed, you need to get breakfast, you need to brush your teeth, you need to comb your hair, you need to, all of these things. And at first you need to give them every instruction, but then by the time as they get more mature, and then finally with my youngest son, he got it at a very early age. He'd set his own alarm clock, I wouldn't even hear him leave. And he'd get up and he'd do all that stuff, and maybe the worst thing he would do is leave behind a little mess in the kitchen from himself fixing a little bit of breakfast or whatever. But at least I knew he had breakfast before he left, and he took the time to do that. So eventually it went from every one of those steps to make sure you leave for school on time. Yeah, I'll do that. And then all of those other instructions got done. So basically, as we mature, we could handle more complex instructions. It's the same thing as the education process, right? The more of an education you have, you go back to work for Nintendo and they say, hey, Lena, we want you to run these tests on these machines, and because you're educated now, you'll know exactly what that means, as opposed to, okay, you need to get this wire and insert it in here, you need to get this piece of test equipment and this is how you turn it on, and you understand? So the computer is really the same way. So this instruction set is very critical on what ultimately the capabilities of it are. Control unit also generates the necessary pulses to carry out the functions specified. What is it that you're trying to do with it? Consists of an address register, an instruction register, an instruction decoder, a program counter, a clock, and circuitry for generating the control pulses. The heart of the computer is the ALU, the arithmetic logic unit. This is what performs math. And quite frankly, all of the magic that's done inside a computer is done simply by processing math. It's all pure math. No guesswork. It also performs logic and all of the decision-making operations. Memory is the area where programs are stored. Input-output units allow the computer to receive and transmit information from and to the world outside the computer. Now the input-output unit is controlled by the central processing unit, CPU. This here is just to kind of show you some memory cells. Sit down for this one, right? This is kind of crazy. Remember earlier I was telling you about that ASCII, and when I hit a key on a computer, it generates really a 7-bit code. ASCII code is 7 bits, and then there's a parity check, so you're really using a total of 8 bits. So for example, to store my full name, Joseph Gryniuk, the letter J would be stored in here in an ASCII code. J-O-S-E-P-H space, which means nothing, G-R-Y-N-I. There's not even enough memory here to store my freaking first and last name. And look at how complex this, by the way, is a simplified drawing of memory. Okay, simplified drawing of memory. To get the data to these memory cells, we have what's called a data input bus. And what this data input bus is, this is the simplified drawing. Here we show it as a big, thick, light blue line. In actuality, it is 8 lines that are interconnected with each of these cell locations. So if we really wanted to draw this accurately, instead of drawing this big thick line, we'd have 8 lines in parallel. It'd get very, very busy very, very quickly. That's the input data bus. The output data bus would have the same thing. There'd be 8 lines coming out of every one of these cell locations. Then we'd also have this memory cell selection line, which selects which cell are you reading to or writing from. So this would be very, very complex. So you got to think about right now with memory. I was just looking at a Fry's ad in the paper this morning, and I don't know, like 6 gig. This is 1, 2, 3, 4, 5, 6 times 2. This is 12 bytes. 12 bytes. You could go out now and buy 6 gigabytes worth of memory for, I don't know, 49 bucks or something ridiculous. It's mind-boggling. So that's not giga, is not million. Because million would be mega, billion. Billion bytes for 49 bucks. And then obviously if you've stored documents or anything, I mean, it amazes me on how much we could store now. Even like on you get a thumb drive, 4, 8, 16 gig, 32 gig thumb drive, and how much you could store on it. Here we can't even store what you're looking at, my first and last name. So these circuits really, really get complex. Very, very complex. So this is what memory cells would look like. The microprocessor is the heart of a microcomputer. The microprocessor contains 4 basic parts: registers, arithmetic logic unit, ALU, timing and control circuitry, and decoding circuitry. They're designed so that an instruction can be fetched from memory, placed in the instruction register, and then decoded. The microprocessor contains registers, accumulator, condition code, program counter, stack pointer, instruction decoder, arithmetic logic unit, timing and control. These are all the functional parts. Microprocessor instructions fall into 9 different categories. This is why I had a hard time in programming. Because it's why I had a hard time in Spanish. I think my understanding of English grammar was somewhat limited. So if I can't do proper English, how the heck am I going to do Spanish? If I don't understand English, how the heck, if I don't do math, how am I going to understand? Am I trying to move the data? Am I trying to perform an arithmetic function, logic, compare and test, shift and rotate? program control. Stack, is it input-output or is it miscellaneous? I'm not saying this to spook any of you because, again, programming has come a long way, but I remember when I was in a Navy school, it was my first computer, I had to write a program that added the number like 2 to the number 2, and I was supposed to get 4. So it was like, and I had to do it in octal. So what was involved is like first in octal loading the number 2 and then storing it in memory, and then loading another number and 2 in memory, and then saying, I want you to go out to this memory location, get these contents, and add it to the number in this contents, and then get the results and store it here. Anyway, by the time I was done, it was like 6 pages of code to add 2 plus 2. And this is in machine language. It's a nightmare. I thought it was the end for me. I thought if this is what the next nuclear warrior has to be, they got the wrong guy. I'll go paint aircraft carriers.
One line of code now for all that.
Yep. So a lot of programming has become somewhat simplified. They were trying to look at our ability just to process this whole thing. And so anyway, I really struggled with this because I think the better math student you are, the better off you do with this stuff. Microcontrollers. This is the big thing now. This is the real. Small devices used to control objects, processes, or events. Used to monitor and control automobile engines, consumer appliances, high-tech toys, music, and greeting cards. I mean, when you get one of those goofy songs on a freaking greeting card, it's a microcontroller in there. It's got to be able to get that contents of memory, process it, play it, and provide an output. And make it sound like the song. Basically a single chip computer. The faucets in here with the infrared detector, there's a microcontroller controlling those. The toilets that flush themselves are microcontroller controlled. I mean, you got computers flushing our toilets now. Fortunately, they're not networked. You know, I don't know what the benefit of that would be, but they are small computers that are able to process, and they could change the setting in there that once you detect that, what threshold needs to be overcome before it flushes. How many flushes could there be in a certain period of time? All of that's programmed in. Microcontroller. In summary, digital computers consist of a control section, an arithmetic logic unit, memory, input-output section. The control section decodes the instructions, generates pulses to operate the computer. The arithmetic logic unit performs math, logic, decision-making operations. Memory is an area where programs and data are stored while waiting for execution. And the I/O units allow data to be transmitted into and out of the computer. Control section and ALU may be included in a single package called a microprocessor. A program is a set of instructions arranged in a sequential pattern to solve a particular problem. Microprocessor contains registers, ALU, timing control circuitry, decoding circuitry, and instructions for microprocessor fall into 9 categories: data movement, arithmetic logic, compare and test, rotate and shift, program control, stack, I/O, and miscellaneous. Computers don't only amaze me, Windows really amazes me. When you think about, you could have a desktop open and all of these applications running seamlessly. I really honestly never thought I'd see the day in my lifetime where we'd have this technology available to us right now. I mean, it really is mind-boggling. Having been there in the early development of a lot of our digital systems, it just truly was exponential growth. I know a lot of you hear that in textbooks and understand that, but you know. And then now when I see things like, you know, what Apple's doing with the iTouch and some of the human interfaces, they're trying to get us away from, because I mean, this is freaking crude, man. A keyboard, a mouse, it's pretty crude. Operating a computer, it's very, very crude. So it's going to be interesting, the next advancement of computers to be able to, I mean, because it's amazing what we can do right now with them. And with microcontrollers, fortunately we have a microcontroller class here. Typically Peter teaches it. And we study a specific microcontroller, and you know, When you buy them in bulk, you're buying a computer for like $1.75. And you could stick that computer wherever you want to stick it, and it's going to sit there and it's going to process data for you. Students a couple years ago, I think you probably heard the story of making the beacon light at my house, my flagpole light. It's a microcomputer. Whenever the power goes off, the thing shuts down. When the power comes back on, it reboots and just picks up where it left off. It's a small computer in there for $1.75 that's controlling that light in a very specific way, not just flashing it. The timing is exact. The code is specific. It's crazy. Any questions on anything that we covered? So this is the end of digital. This is the end of ELEC 120 lectures. Basically, Kaylina, you could coordinate now how you want to take the quizzes now that the lectures are all done. Just let me know what you